So first law and the energy. So we're going to talk about mechanical energy, then work, then power, boundary work, because we have pistons and cylinders and gases expanding and compressing, very important. And then we're going to talk about heat transfer, just like a work transfer, energy transfer across the boundary of our system. Then we'll do a balance of energy, because energy is conserved. That is energy is a property of the system. I didn't define it yet, and then it's conserved. And we'll only do it for a closed system. And then we'll talk about cycles. Kinetic energy. It's a form of mechanical energy. Somebody says, could an object have kinetic energy? This object. Any object. Grab your shoe off your foot, right? Or so your book off the table or something. Say, that's an object, that's my system, the focus of the study. Could it have kinetic energy? And how would I, as an engineer, quantify it? You would say, well, tell me its mass. I have to know its mass. If I don't know its mass, how am I going to calculate its kinetic energy? And then what else do I need to know? Its speed, the magnitude of its velocity, or velocity, whatever you want to call it. V, true? Now, m times v, is that the kinetic energy of my object? No, that's my linear momentum. It's an important property. Linear momentum is a very important property, just like mass is an important property, and speed is an important property, and the velocity is an important property. But the equation for kinetic energy, 1/2 mv squared. You know what? You guys got that down perfect. That's the kinetic energy. True? Right. So that's a form of mechanical energy. The mechanical description on energy, it's as if it's organized. All of the molecules in that mass are all going at the same bulk, macroscopic V, speed. True? So it's organized energy, kinetic energy. Potential energy, or specifically gravitational potential energy, because we used Ke, 2 letters, for kinetic, we don't want to use 3 letters for gravitational potential energy, GPE. We just want to use PE, potential energy. So somebody says, yeah. An object can have potential energy. The object at this point in time has some potential energy. The object at this point in time has some potential energy. Which one had more? The higher one. You already know. So what's the equation? How does the system's MGH or MG Z. I'm sorry? We could talk about a system being a spring and compressing the spring. Let's get to that later maybe. Okay? But right now I'm just talking about a mass traveling at a velocity, and it has energy. And then the potential energy. Those 2 forms of energy. All right. Now we get to the conservation of energy principle, especially the conservation of mechanical energy. If I take that mass, it's in a gravitational field, G downward. Let's put Z upward. I know that always is a challenge, but higher Z means higher elevation in the gravitational field, and the gravity wants to pull it down, okay? So that's our direction of Z, positive upward. In a gravitational field, there it is. Let's start at state 1. If I let it go, sometime later, I have no force supporting it or holding it up there. Where will it be after some time? After I let it go, it'll be below. It'll be at state 2. And, believe it or not, the sum of the potential energy at state 1 plus the kinetic energy at state 1 is equal to the sum of the potential energy at state 2 plus the kinetic energy at state 2. Let's say we started at rest. State 1, it's at rest. If it's at rest, what would this be? 0. And maybe we even redefine our coordinate system such that Z0 is right there. The object is at 0 elevation at time 2. At the final state. What would the potential energy be? It could be 0 in that case right there. So we could have a transformation of energy between 2 mechanical forms, potential to kinetic. Not very surprising, is it? Let's do this. Let's go back and see, how did I ever get this equation? How could I ever start from some foundational principle in science and engineering and get the conservation of mechanical energy equation, where the PE and the KE fall out in the 1/2 mv squared and the mgz, and its sum up is equal to 0? How do I do that? How would I start that derivation? The derivation's in every physics book and probably every thermodynamics 1 book. We start with F equals ma, right? Just start. That seems to be the bedrock where you start a lot of analyses. So let's start with there. The sum of the forces on my object, called the mass, is equal to the mass times acceleration, Newton's second law. In this case, how many forces do I have on this object? 1, and what is it called? It's the weight, and it's equal to m times g. True? I know that I'm holding it up until time 0 when I start the drop, but right when I start the drop, I'm not holding it anymore. So I was able to keep it at 0 speed until I let it go and started that state 1. Okay? So this is m times g. Now, we want to be careful, because is this making it want to go in the positive z direction or negative z direction? Negative, okay. And now it's a little trick. And over on the side, the little trick, maybe I change color or something to remember. It's like, what is acceleration compared to velocity? Is it equal to the time derivative of velocity? How many people thumbs up? Very good. But I want to talk about the velocity. I know I use time always, but I want to know the velocity at state 1 and at state 2. I want to know it as a function of position. Do you think somehow I could quantify the velocity as a function of position as well as function of time if I wanted to? But think about that. I could put it as a function so that my independent variable of interest is z, not t. Okay, if that's true, could I take the derivative of v with respect to z, then multiply by dz dt? And that's acceleration. Calculus. I thought we were done with that class. Are we done with that class? No, it always lives on. Okay. But do you see what I've done here? Every textbook is done. I'm just following the textbook. You've probably seen this derivation before, true? So let's go ahead and put that right up in here. I'm going to put the dv dz right there, but I think I know what dz dt is. Just like acceleration was the time derivative of velocity, velocity is the time derivative of position, and z is just my position. True? Okay, let me think about this for a minute. So v is equal to dz dt. True? Okay, that's good. There's one thing I need to do, though, and that's this negative sign that's going to be bothering me a little bit. Okay, so if v is positive, which way is the object going in the positive? If v is negative, which way is the object going? Falling. It's falling, not rising. True? So dz dt is v. True? So I'm going to put that right in here. That goes right in here. V. dv dt. All right. Now what I do is I'll go ahead and separate. This is your ordinary differential equation. And you have some initial condition that v at time 0 is equal to some v naught, or v1, right? We're going to state 1 and state 2, right? Or v at z1 is v1. It's initial elevation. Remember, we're putting it not in terms of time, but in terms of position. Okay, elevation, z. So this is my initial condition or boundary condition because it's not time is my independent variable, but space is my independent variable. And this is my differential equation right here. Well-formed mathematical problem. You can do it. It's not the Cal 1 or Cal 2. It's the EA 1 class. EA 1, Engineering Analysis 1. All right, so the big strategy, it's like you come out of Cal 1, differentiate, 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 maybe chain rule, chain rule, chain rule. And then you go out of Cal 2, integrate, integrate, integrate by parts, integrate by parts. Come out of differential EA 1, separate, integrate, separate, integrate. That's all you got to do. True? Separate, integrate. So let's do the separate and integrate. mgdz minus equal to mvdv. Integrate. True, true. We're going to have the same lower limits on the integration and the upper limits, and we'll take care of the boundary condition in our limits. So what about this? It starts at V1, where the elevation is Z1, true? It ends at V2, where the final is Z2, true? All right, so what do we get? We get...
Are both masses constant?
Yeah, the mass is not changing. Don't want to cancel them, though, because we're going to need mgz and then 1/2 mv squared. Otherwise, I got to put them back in later. But you could cancel, but then you got to put them back in because we want this equation right here where this PE is that with the m. All right, so mgz 1 minus z2, taking care of the minus sign, and then 1/2 mv2 squared minus 1/2 mv1 squared. Did I do that right? So if I bring the 2's on both sides over here, this is KE2. If I bring this one over, I'll bring it so it'll be KE2 plus PE2 equal to KE1 plus PE1. Does that make sense? This was my kinetic energy 1. I bring it to that side, takes care of that minus sign. And mgz1 is right there. And the minus sign's taken care of when I bring this one over to that side. True? Did I do it successfully? So you just rederived. How many times have you seen that? High school, maybe? Physics? Definitely. Dynamics? You're maybe in dynamics now. Maybe you've already passed dynamics, but there you go. So that's the conservation of mechanical energy for free-falling objects. I don't want to solve a problem. Work. But you need to solve problems. True? Work. Think about work pushing a mass without worrying about gravity. Just push it horizontally in a gravitational field. So just pushing it along, okay? Now, you might push it where there's some friction. Or you might push it where there's friction with a solid that it's rolling over or sliding over, or that's through a fluid that has some friction so that there's some drag on it, some resistance to it going in that direction. So we introduce a coordinate system like this. This is x. My object is here. Maybe I start it at x equal to 0. It doesn't really matter. This is x equal to 0, increasing x equal to 0. I can write, come on now. There you go. And then we put a force on it like this, F. Okay? If I just put a force on it, okay, and that force, don't even have the viscosity. Forget the viscosity. Forget what I said about that. Just have the force F only on the object. At a later time, what will the object be? It'll be over here at a different x, true? And it'll be moving at a different speed. Maybe when I started, it was already moving at v1, but now it'll be moving at v2, true? So we start from Newton's second law, sum of the forces equal to the mass times the acceleration. The only force that I'm going to put on there is the force pushing to the right in the positive x direction. Forget what I said about viscous, okay? Sorry about that. Later I'll talk about pushing an object through air, aerodynamic drag, power. That's where my mind was. Equal to the mass times acceleration, which I can express as dv, dx, dx, dt. True or false? Remember that little trick? I said A is dv dt. A is dv dt. But I think that I can also express v as a function of x. So I can say dv dx times dx dt. That's equal to A. Hey, from calculus, I think I remember this. What was the name of this little trick again? Chain rule. See? Was that in Cal 1 or was that Cal 2? Probably, yeah, it was all a big blur. Okay, so there you go. And this is now called V. Isn't it V? dx dt? That's right. It's the time derivative of the position. X is our position. So this becomes V. That's my nice, what do I call this equation? ODE, ordinary differential equation, with either a boundary condition or initial condition, depending if time or space is what's my variable, independent variable. I want to solve it. I learned how to separate and integrate. Separate and integrate. F dx equal to mv dv. That's the separation part. Now the integration part. Now, this comes in at 1/2 mv final squared minus 1/2 mv initial squared. Somehow the kinetic energy changed. Somehow the final kinetic energy KE2 in the way I'm presenting it is greater than KE1 because I'm pushing to the positive x, right, on the object as it's going. True? What do we call this over here, this integral f dx? It's work. That's work, mechanical work. W is a symbol given for work. So we learned and you learned, how many people recall fuzzy? W is equal to integral f dx. Thumbs up. How many people say, hey, I even learned a more complicated version than that? You have the scalar version. I learned the what version? I'll give you a hint again. I learned the scalar version. You learned the vector version. Vector version. It's the vectors, right? And so if I have force as a vector, I have the little displacement, sometimes ds, as a little displacement vector. And if I have little vectors, I have to do a dot product, a vector product known as the scalar vector product or the dot product, right? So if the force is aligned with the direction of the motion, no problems. The two just turn into a scalar equation. If my object's like this, moving like this, and the force I apply is like this, and it's perpendicular, does the F dx equal anything? Is there any work in that case? Zero, 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 because this dx is 90 degrees. What was the fancy word for they're perpendicular, they're what? Orthogonal. All I'm trying to do is improve your vocabulary. I'm not helping you spell these words. I'm just helping you pronounce them. All right. So this is an equation. The work is equal. So what we have is we have this concept of work where it's pushing a mass, and I'm neglecting gravity, and it's just pushing it along the horizontal. And we see that that work tends to change the kinetic energy of the object. What do you think the next one is? Put in gravity. Put in gravity, right? So, oh boy, I don't like this coordinate system. I don't like the, but here we have to do it. Okay, let's put z going up, and somewhere is z0. I'm going to start the mass down here at state 1. I'm going to put the mass up here at state 2. I'm going to put a force that's aligned with the positive z direction there. And the motion is going to be going up, up, up. It's just the way I wrote it, okay? You could write it the other way and go down, down, down. But one of the things that you have to worry about is, guess what's always acting on that mass? In the gravitational field, G. The weight, the force known as the weight, the gravitational weight. True? Oh boy, I don't like this problem, right? But I want to now get an equation where I have that work, the integral f dz, not dx, but dz now, right? Because I'm going f in the direction of dz. Changes the kinetic potential from the beginning to the ending state, right? Or I could write it like, work is equal to the change in kinetic plus the change in potential energy, where the kinetic is Ke at 2 minus Ke at 1 minus plus Pe2 minus Pe1. How would we go about deriving or showing this equation where I have work now pumping energy into the system? It could be increasing the kinetic and increasing the potential energy of my mass. My system is my mass. True? How do I show this equation? Start with F equal ma. True, but I have a sum of forces. Hey, this time I have two. What two forces do I have? The F pushing up and the mg coming down. True? The weight is in the negative. All right. What do I do with that acceleration? Z, and then put the v right there. True? Did I do that step okay? Thumbs up if you follow. Okay. Now, let's do this. I have now what type of equation? Ordinary ODE, ordinary differential equation, right? And I have some initial condition. I'll just put those in with the limits of the integration. What's my strategy? There's some faculty, all you have to do is say, separate and integrate. Oh, I love you. This is so good. You're so smart. But that's what I'm looking to do, is help you along. So we separate. So we have F dz. What do you think that's going to turn into? That's going to turn into work. You're good. And mvdv. True? Now we do the integrate part. Integrate, integrate, integrate. Your initial or boundary conditions will be taken care of in the limits of the integration, if you haven't seen that done before. So all we do is we call this our work. It's by definition, that's our work. That's the work that went into the system from this external force applied to the system, right? It's positive in. It's going to, okay, let's do this math here. Minus, we get the mgz, this is 1 and 2, 2, minus a minus, so it's a plus, mgz1, equal to, or you know what I should have done? Even faster. Equal plus. Thank you. You saw that, didn't you? Okay, so let's do this. Now everything else other than the work is on the right-hand side of that equation, and it makes it a little easier with the mgz2 minus mgz1 plus 1/2 mv2 squared minus 1/2 mv1 squared. I stop, I pause, because I know sometimes I make mistakes, and students, have I made a mistake? Where am I okay? How many people have followed me so far and you know, you verified it? There's no mistake. Good, good, all right. So this is the PE2 minus PE1. This is the delta PE. This is the KE2 minus KE1. That's the delta, delta KE. So the notation is whenever you have a delta, no matter what it is, delta x, it's x final minus x initial, or x second minus x1, okay? So that's what we're doing here. Does this look good? Let me ask you a question. If I wanted to calculate the work, I would go and how would you calculate? Would you go back and say, from very first principles, if you're not going to tell me, this is an energy balance equation, but you're not going to tell me how anything on the right-hand side changed, I'm going to have to calculate work from first principles. I'm going to have to go back and calculate work as the integral f dz. True? Somebody says, I'm giving you f as a function of z, integrate it and get me the work. True? Okay. Let me ask this question. Would you always get a positive work, or could the work be negative in some cases? It could be negative? And how? In what case would it or could it be negative? Change the direction of F. True? So F is now down, but the motion is up. True? Right? It's the same concept. Maybe I'll give it a new page here, insert new page. It's the same concept of, here's I don't know, some object like a car, right? And you're going to push it. Here's some wheels on it on the road. And you get behind here and you start pushing on that car and it starts to go in that direction. You're pushing in the direction that it's moving. Are you increasing the kinetic energy of the car by pushing in the direction it's moving? Are you putting work? You are supplying the external force on that car. Are you putting work into the car to? Yes. All right. Now your buddy, they have 5 of them over here. All right. And they're pushing the other way. Who's going to win? Okay, you're really going to be pushing hard, but the car is going this way. All right? Right? You're not putting positive with her work. Maybe that's a bad example. You're going to get run over. All right. Let me think. Anybody have another example? Friction is negative work. It's a dissipation. So if a bullet or some object comes out, if I throw it and it's going this way, and now there's a drag force on that object, it's in the opposite direction of the velocity. And so it'll be slowing it down. It'll be doing the negative work, dissipating. Okay? All right. Let's press forward. So there's my pushing an object through the viscous fluid. Thank you. Good one. So the force that you push on, if I'm pushing it at constant speed, is balanced by what we call a drag force. True? So your car is going down the road, neglecting the rotational resistance and friction with the tires. There's a lot of aerodynamic drag on your car. True? And the engine of the car has to produce enough power to produce enough constant push, I know it comes through the tires, on the car to keep it propelled down the road at a constant speed of, you obey the law, 60 miles an hour. I've seen you on the road. You do not speed. So you're only it's posted 60 miles an hour, you're only going 60. Other people are passing us. We don't know who they are. But that's other people. But they're going at a constant speed of 60 miles per hour. True? There's an aerodynamic drag. There has to be a constant force supplied to keep you going. All right. Before I do that, what is the... well, let me jump down here. What about now power? There's a difference between work and power. True? Because work would be the integral of f dx. So you'd say, okay, it's this force supplied over that mile. That gives me a work. Okay? But what we have is we have this object moving at speed v, right? We want to know the power, the rate at which work is produced by the engine to overcome the friction, the viscous drag on the car. What is that equal to? It's the time derivative of the work. The work was f dx for a constant f it's equal to what? How many people recognize that equation? So what is it in words? It's the product of, the power is the product of the times the speed, right? All right. Okay. Okay, we'll get to where the aerodynamic drag, this is in the car application. The aerodynamic drag is often proportional to the speed squared by itself. And when you have the aerodynamic drag proportional to the speed squared, and then you multiply by speed again, you find that the power goes up as the speed cubed. Right? When you're theoretically driving your car and you're going, 60 miles an hour, and you say, I don't care if it costs me a little extra gas. I want to get there faster. I want to drive 90 miles an hour. Right? That's not safe. You'd never do that. But theoretically, the force of the drag is proportional to the speed squared. True? So if in case 1, force of the drag when you're driving 60 is equal to a constant times the speed of 60 squared, the force of the drag when you're driving 90 is the same constant times the speed of 90 miles per hour squared. See that? Get rid of the constant. We find that that's equal to the force of the drag first case at 60 miles an hour times the velocity, v2 over v1 squared. So what percent increase is the aerodynamic drag if you change from this speed to that speed? It's the ratio of the speed squared. So if somebody has a calculator, let's run the example, please. Do you have a calculator? Do you have a calculator, somebody? Put 9 over 6 and square it. 90 miles an hour over 60 miles an hour and square it. Go ahead and do that, please. What number do you get? 2.25. Your engine has to work a lot harder, okay? Because that's the drag. It's more than 100%. It's 125% greater. Is this right? 9 over 6 squared is that number? Did you verify it? All right. Now your engine has to put out power, right? So the power for the second case going 90 miles an hour is the same type of constant, but it's the speed squared versus the first case when you're going 60 miles an hour, the same constant. That's cubed, sorry, cubed. So we get the power increase is equal to the V2 over V1 cubed. Do the same 90 mile an hour versus 60 mile an hour, but cube it instead of square it. What number do you get? 3.375. That's why my car can't go that fast. I don't have a big enough, strong enough engine. It's in its dream. At night I can see it sleeping. Like, you ever have a dog or a cat and they're sleeping, they're going through a dream and they're twitching, just chasing something, laying there sleeping. We have dogs. Anyway, my car does the same thing. I'll see it out there sleeping in the driveway and it'll be like dreaming it's going 90 miles an hour. It can't do it. There's no way. The engine's not powerful enough. All right. There's more to this story. Anybody remember a president named Jimmy Carter? That was before you were born, I think. I was alive and voted in the election when that was my first election I was able to vote in, so that puts my age out there, over 50. But basically, Jimmy Carter came and there was an energy crisis. There's always energy crisis. But anyway, there was an energy crisis, and he changed the miles per hour nationally on all of the roads. And he threatened to take away your state funding for highways and support unless you complied. So guess what every state set as their maximum speed? 55. I challenge you to drive from here to Tallahassee or to, I've driven it. When I was young, your age, I had to, 55, and the state troopers in Florida had no mercy. I had to drive all the way to the end of I-10, which is in Jacksonville, visit my friend, 55. No wonder I have gray hair early. I'm serious, it was 55. And why did he do that? Right here, because the lot lower energy or power consumption to push buses and trucks and cars through the air at a lower speed than a higher speed. Theoretically, you're going to save a lot of energy. But we got rid of that. Thank you. I did not like driving it. And Illinois was the worst state, too. Illinois was one. Oof. Pennsylvania was another one. I don't know. You're too young. Those are big states. 55 miles an hour is very slow. All right. Now let's go to rotating or turning a shaft. If I have a shaft, shafts are often used to transmit torque. Let's put this symbol, torque. That's our torque, okay? And then you can rotate a shaft through an angle of rotation, theta. Theta is a good angle of rotation. We'll let the angle theta be in what type of units would theta be in? Radians. See how much you've learned? So what is the work to turn a shaft of constant torque no matter how far I'm turning? It's the same torque. It's uniform torque, just like same force no matter how far I pushed it. Through an angle theta. What is the equation for the rotational work? Would it be integral tau d theta, which if they're constant, it's just tau delta theta, right? Just like if f is constant, it's f dx. True or false? How many people have already passed dynamics? Did you not do something like this for rotational dynamics? Yes, say yes, please. Yes, thank you very much. All right, now guess what? If you know now the work, can you do the power in a rotating shaft? Power in a rotating shaft. That shafts transmit power all the time in rotating. Are you an aspiring mechanical engineer? You think shafts and rotations and power and torque are your domain? Or are you going to say, hey, is there an electrical engineer on the staff to answer that question? No, come on, right? So what is it? Do you know what it is? What's the power? Do you know it? Oh, please. Weren't you my aero guy? You know the aerospace, the what, Cyberjet? Yeah. Come on now, you got to know this. You're a gearhead. How many people call themselves gearheads? I'm a gearhead. I've been into engines and play with them too many times. I'm getting too old for it. Dropped too many transmissions on my back laying in the dirt. Come on now. It hurts, I know. What is it? Come on. Anybody know? Who wants to be a mechanical engineer? You don't want to be a mechanical engineer? You don't want to be a mechanical engineer? Come on now, raise your hand. You want to be a mechanical engineer? This is going to be your domain, right? Otherwise, go electrical or civil or something else. Guess. 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 Somebody guess. What is the power? What is the equation for the power transmitted in a shaft that's rotating? Rotating shaft. What is the equation for that? It's really easy. W dot, we'll do it like that because that's our symbol for power, and W is our symbol for mechanical work. And you take the time derivative, tau is the same, and you have d theta dt. Guess what? We'll call that something else. Instead of omega, how that, that's the answer. Anybody ever seen the book and it does that? What is this symbol used for? Angular velocity or angular rotation rate. Absolutely. And what units does omega have to be in? Radians per second. Does that really work? Do the units really work? If I put in my units in SI, Newton meter for the torque. Good units, thumbs up if you agree. Oh, come on, not enough thumbs up. Hey, by a couple more days in this class, hopefully everybody will be ready to give me a thumbs up. All right, even in the back. Even in the back, okay? I can see back there. Times a radian per second. Do you think that gives me power? Come on now. Okay, so what is Newton times a meter? Joule. What is a radian? It's dimensionless, length over length, but we want to assign something to it, so we talk about our radian, but it's the arc length over the radius. That's what a radian is defined as. Arc length over radius. Okay? It's a measure of rotation, angle. Okay, so it's really no length to it. No, and so now I have a joule per second. Is that a watt? Yes, it is. True? Hey, let's get this down. Last one, electric current. I didn't leave enough room here. If I have a battery, has a negative post and a positive post. Let's just do DC, forget the alternating current. Right? And it's a certain voltage battery. Sometimes you put E for EMF. The electromotive force measured in volts. So it'd be a 12-volt battery, 36-volt battery, whatever. 9-volt battery, okay? And then I have something flowing that way, right? Current. Current, true? Current. So the current, what symbol would I like to use for the current? I. And what units for the current? Amps, amperes, true? A, amperes. So E is the electromotive force measured in volts. I is the electric current measured in amperes, right? I know the symbols and the units are challenging at times. But what is the power supply by this battery if so many amps are running through it and there's a voltage gain through the battery? The power is being supplied by the battery. What's that power? Oops. E times I. True? Now, if this runs over to a resistor, and that resistor, we'll call the resistance symbol R, measured in what units? Amperes? No. Ohms. Measured in ohms. True? Ohms. True? Now, if I want to know, it's just a simple system like this. The battery supplying the energy, the resistor is dissipating the energy, right? It's going to get hot and move off with the heat, but let's not worry about that right now. Let's just talk about what is the W dot dissipated, the electric power lost or dissipated in the resistor. Now, no, I'm not going to put a negative. I'm just talking the magnitude of it. Now, what is that equal to? Is it the voltage drop across the resistor times the current through the resistor? Is it that? What? I have a voltage drop across the resistor, true? All right. I have the current through the resistor, true? What is the power dissipated in the resistor? Voltage drop times the current. That's all. True? So it's also equal to E times I. True? Believe me, so many double E's have abdicated electric power that the mechanicals have to know it. What's the new department name in electrical engineering? Electrical and computer engineering. They now not just give electrical engineering degree, they give a computer engineering degree. That's a shift away from power to information, communication, and digital, blah, blah, blah. So guess what in your job? The electrical engineer says, hey, I'm going to do this, buddy. That sounds like power and energy. That's your domain. Yes. Yes, you can't, you're getting more and more of it as mechanical engineers. True? So, again, I say resistor. This is so simple, really, and it's not even the alternating. not a no phase shift. None of that stuff, okay? It's just E times I. But we also know somebody's law that relates the resistance omega and the voltage and the current. It was Ohm's law, right? I need to erase some space here. Sorry about that. OHM. Did I get that right? Ohm's law. What is the equation, Ohm's law? E equals IR. And I heard some people giving me answers which are the combination. The power dissipated in a resistor can be rewritten using now Ohm's law. How can it be rewritten? I squared R as well as E squared over R. Hey, it's just like a piece of gold, right? Little tarnish, you rub it a little bit, it shines. That's what your knowledge is like, right? You're like, just get the little tarnish off of that cobweb up in the brain, and there it is, all waiting to shine. So there it is, okay. Now don't forget, power is very important. Some students, I don't know why, in Thermo 1, they just like, nothing. And the other thing is one time I had a question I gave on an exam, and I took off points, and I would not give the points back to the students. I said something like, so many kilowatts are transmitted in the shaft. The shaft is rotating at this speed. Calculate the torque in the shaft. I thought that was a giveaway. They gave me the torque, numerical, and they reported the units of torque as what? Take a look. What did I say were the units of torque? That's the units I wanted. Some students, I would say a third of the class, I don't know, when I gave this question on the Thermo 1 first exam, gave me the units of torque not in Newton meter. What did they give it to me in? You can probably guess. Come on. Joules. There's nobody. I'm trying to prevent them from being laughed out of their first day of work. When somebody says, hey, what's the torque, the shaft, blah, 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 machinery. So many joules? What? So many joules? Well, look at the SI units, Professor. A Newton times a meter. Yeah, but torque is a force at a distance. It's inch pounds. It's foot pounds. Newton meters. Now, some people get really particular, and they say the meter has to go before the Newton. I'm not in that camp. Okay? Or the inch has to go before the pound, or the pound before the inch. I don't even remember the debate. I gave up on it, said, look, I think I can be understood. But believe me, there's some purist out there. I'm not one of those, but I'll have to go look that up. Whether it's a Newton meter or a meter Newton is the correct way to write it. Okay? But let's press forward, unless you have a question. Work is one way to do what? Transfer energy. Now, we had a system. Where was that energy coming from? The surroundings. It was being transferred through the boundary into the system. The system had either greater kinetic or greater potential energy. Although, if the force was retarding its motion, right, then there was a transfer out. But we'd like to work with it in a lot of cases, especially in the beginning. But work is simply a transfer, an energy transfer. It's one way of other ways, too. We're going to do heat transfer. Here's our thermodynamic definition of work. Work is done by a system on its surroundings. It's basically getting into the sign convention that we want. We'll talk about the sign convention. If the sole effect on everything external to the system could have been the raising of a weight. Raising of a weight? What does that have to do with work? It's basically getting at that idea of organized energy transfer. And if you're very organized, it's mechanical. You can do something like raise a weight in a gravitational field. And this definition is very popular and it's out there. Okay, but just think, the other transfer we're going to get is heat transfer. Maybe that's the next slide. Let's move on. No, let's talk a little bit about why work is not a property, but it's a transfer of energy. if it's what is its characteristic of a property? We talked about it before. If I said I want you to tell me the volume final versus the volume initial, that's the change in the volume. All I need to know is the volume final, volume initial. Take the difference. I have the change in volume. Volume is a property of the system. I didn't have to know anything about the path. But I say, okay, we started at state 1, we went to state 2. I want you to tell me the work that was done. You've got to tell me the path. How was F varying as X changed from X1 to X2? Was it constant? Then I can do the calculation. Or did it change? So you have to know the path. You have to know the intermediate steps. Okay. So because it's not a property, we have special notation for things that are not a property. Delta V is a good change in the volume. Will you ever see delta W or W2 minus W1? Bad notation. Bad. Because it's not a property. Don't treat it like a property. What we have to do is we have to say work from 1 to 2, or work 1 comma 2, or work 1 to 2. Something that's not work at state 1 and work at state 2. Because work is not a point function. It's a property that depends on the path, how F varied as the system changed. So these are okay. This is, I don't like this one. This one's okay. Sometimes they'll just do work 1 to 2. Well, it looks like work 12. But you have to live with it, okay? I prefer this one a little bit, and I'll probably write it every now and then because it's clear. It starts at 1, ends at 2. You know, it's like a pre-note subscript and a post-subscript on your work. But it's not used in the book. All right. There's a sign convention for the work. Engineering thermodynamics was all about heat engines. What about a heat engine? Heat engine is a device where you burn something to turn something which lifts a weight in a gravitational field, right? So you supply heat by burning something created hot, and you supply heat transfer to it, transfer the heat. The purpose is to produce some work so that it can raise the weight in the external field. So work out of our system is good. That's our beginnings in engineering thermodynamics. And still the mainstay in a lot of systems, it's power production, right? This now is a cold system, and you have to dump off some heat from the hot. You have to dump some to the cold in order to make it work. That's a limitation from the second law of thermodynamics. We'll get to that limitation. Okay? But the workout is positive. This is positive. If it's greater than 0, it's positive out of the system. Let's talk about gas that's trapped in a piston cylinder apparatus. It starts at state 1 here. It could be expanded. The gas is the system. See the dashed line? The gas is the system. It could be expanded. Maybe this is the final state 2, where here I'm still showing you where the piston started. True? If the gas is the system, is it a positive work out when the gas expands? It's very hard. This is very, very hard. Is the piston part of the system? Nope, the piston is not part of the system. The piston is part of the surroundings. Look where the dashed line is. It ends at the face of the piston. The face of the piston is part of the surrounding. This gas is the system, and it pushes back the piston. It does work pushing it back. It's a positive workout of the system. All right? Compression of the gas. It's a negative work. This is a negative work. This is a positive work. Right? In order for me to calculate the work 1 to 2, or the work for this expansion process, what do I need to know? I need to know the pressure at the face of that piston as it moves back from 1 to 2. As that gas is expanded, just using your intuition, do you think the pressure would more naturally go down or go up? The gas has more room now. So the gas pressure is probably lower. So the pressure on the face of the piston is probably lower. True? So if I made a property diagram, this is the pressure axis, the velocity, not the velocity axis, volume axis, true? And I plotted pressure. I started here at a high pressure. I went to this volume right here. It probably went down. And now if I had the pressure volume axis property diagram, and I started here at that same pressure, and I compress it, what do you think is going to happen? Go up. It's going to go up. All right. Let me ask this. This diagram, I think I have it too cluttered. Let me go to the next slide. All right. Let me go back to this piston cylinder. It started here, right? And then it ended over here, true? At a lower pressure. I want you to calculate the work done by the gas as it pushed back that face of the piston, as the gas expanded. You'd say, Professor, I only know how to do the work of a force on a mass or a force on an object. True? You say, Professor, I can calculate the work if it's F dx. True? Okay, do this. If I multiply this by A and this by A, what is the force on the face of that piston per unit area of that piston? Pressure. This is the pressure. The pressure at the face of the piston from quasi-equilibrium is the pressure anywhere in the gas. It's only one pressure in the gas at any instant as it expands, right? We're not talking about, hey, the pressure in the gas at the face of the piston is a lot different than the pressure over on the other end of the cylinder. No, it's the same pressure everywhere. It changes as the gas expands. It drops. And what is the area times dx? Volume. So think about, I have my face of my piston and it sweeps back, its area. It sweeps back dx. That's a change in volume. It swept the volume. So the work we can calculate by the integral p dt. That's why we love these diagrams. We love these diagrams. So all I have to do now is go right here and calculate that work. Now, when you were in Cal 1, they really didn't show you any graphical means to integrate things, did they? Or did they? Maybe they did. But visibly, if this is zero pressure, and this pressure is going up from there, what is the area under the curve, as you're going like that, visually represent? The work. That integral is the area under the curve. The integral f dx is the area under the curve, as long as you're going in that direction. If you go the other direction, it's a negative of it. All right? So let's continue on and do that next one too. So we started here, but now it went smaller, so the pressure went up like this. Maybe I should continue here. Maybe the pressure went up here for compression. This is 1 to 3. 3 was here. 1 is here. 2 is here, right? This work is going that way, and it's not expanding, it's compressing. So it's a visually image of the magnitude, but it's the wrong sign. So the sign is negative for that. Okay, somebody says, can we calculate the work by integrating the little amounts of work done in infinitesimal little expansions? Yes, you can. But because there's such a distinction that we introduce a new symbol, the Greek lowercase delta for an infinitesimal amount of work. Just like dx or what's dx? Infinitesimal displacement. Or d something else, dv, right? Infinitesimal change in the property. But because we want to, hey, look at, work is different than volume and pressure. It's not a property. So we want to have a distinctive notation. I didn't make it up. It's out there in every thermodynamics textbook. A distinctive notation for a small amount of work. And what do they use in front of it? A Greek lowercase delta. That's what it is. Okay? So now guess what this is equal to? P dV. So a small amount of work is equal to the pressure times the volume change, the small volume change. All right? All right. So polytropic process. Polytropic is a fancy name. Just get used to it. It's a fancy name to say any process which can be described by the equation PV to an exponent n is equal to a constant. That's it. Somebody says a polytropic process. Okay, I understand that. PV to the n. What is my n? N could be 1, n could be 2, n could be whatever. Often n is around 1.4. We'll learn more about entropy, isentropic process, but when you take an ideal gas and you very rapidly compress it, it doesn't have a lot of time for heat transfer, and you do a pretty good job of doing it reversibly such that you could rapidly expand it again. And then the pressure-volume relationship is such that this N is about 1.4 for diatomic gases, like air, O2, N2. It's a diatomic gas. So that's at room temperature. So what we have to do is we have to put onto a pressure-volume diagram and think about, okay, maybe I start here because it's easier to expand conceptually. Remember, that's a positive work. That's how you learn to integrate. You never learn to integrate where you're integrating from x1 to x2, integrating backwards. You know what I mean? Your instructor would say, look, this is the x direction. I know, but this was my initial state x. This is my final state x. It's going that way in the process. The instructor, in math would probably correct you. Say, no, you got to turn it around. We always integrate from in that direction. True? So anyway, so let's consider expansion work. And that's a positive work because it's expanding from state 1 to state 2. If I have PV to the 0, ooh boy, or I have PV to the 1 is equal to a constant, okay? Or PV to the 1.4 is equal to a constant. What do those curves look like? What does this PV to the 0 look like if I'm going from V1 to V2? Straight line, you're absolutely right. It's a flat line, and there's state 2. All right. How about PV where the n is 1? It's like when they plotted a function f is equal to x times y, and this is the y, this is the x, and it was equal to a constant. Maybe it was equal to 5, right? If it was equal to 5, you have a certain line, and it goes like this. It's asymptotic to both axes, right? And then if you lower the constant, it gets closer and closer in. And if you increase this constant, then it gets further and further out. But all of those curves asymptote to the xy axis and the y-axis. That makes sense? Anybody want to give me a mathematical name for that type of curve? It's like exponential on both axes, but it's not exponential. Sinusoidal? No. Hyperbolic tangent? No. Polynomial. Quadratic. Y is equal to mx plus b, a straight line. No. Anybody? Hyperbolic. Yeah, that's it. So anyway, hey. Now, what about if this coefficient is 1, then you can kind of project it back like that and project it down like that, but it has a belly to it, okay? It's not a straight line. It has a concave upward shape to it. Now, what about if the exponent's 1.4? 1.4, okay? What does that look like? Let me just ask you a question. It could come in with 2 above the case where PV is 0, would end at the same volume change, or it could come in with the 2 below. The pressure could be below, right? How about you tell me which it is by doing some doodling on the side, and I'm going to pause because I want to get at least 5 people to get that right. It's a tough question. This is a very tough question. Then why do you ask it? I don't know. All right, thanks for making that fix right there. Now we're going to go ahead and vote. So let's do a show of hands, and then I'll just tally up. So those that think this is the correct answer, that the state 2 is going to be higher, the pressure at 2 is going to be higher, in this case, PV to the 1.4. Nope. Everybody else down here? The whole class, unanimous. Well, wow, that's pretty good. Either something's going on. Why? Divide by a bigger number? That's pretty good. Yeah. So you're right. So that's the way it goes. It'll come down. Okay. Maybe you saw the trend. PV to the 0, PV to the 1, PV to the 1.4. Let's see. You know, if you ended at the same V with a PV to the half, you'd be somewhere in here probably. All right. What you have to do is you have to be able to take this equation and analytically compute the work for the polytropic process. So let's see. I want to compute the work from 1 to 2. It's the integral of the pressure dV from V1 to V2. Okay. How do I do this? Well, here's my general equation. So what I do is I just say let that constant be a big C for now. And I say that equation allows me to get rid of this P and replace that P with C over V to the N. True or false? Okay, that's the first good step. Now, is that equal to C to the V to the minus N dV? True? Okay. Integrate V to the minus N. What do you get? V to the minus N plus what? Minus what? Plus 1 here. Okay. And then we put, what do we put over here? Is that it? Thumbs up if you agree. Okay, don't be steamrolled if you disagree. You're ready to go. Now we evaluate that at V1 and V2, correct? Okay, so now we're going to have the constant over 1 minus n times V2 to the 1 minus n minus the constant V1 to the 1 minus n. Did I do that right? Does it look okay still? This constant right here, I'm going to replace by P2 V2 to the n. Can we do that for that constant? And for this constant right here, replace it by P1 V1 to the N. All you did was take this equation and write it 2 times. Constants equal to P1, V1 to the N, or constants P2, V2 to the N. And so it was more convenient to use that form of C there and that form of C there. True? Follow? So what can I do with the V to the N minus N? Gone, right? Minus N, V1 to the N. So we calculate that the work is equal to P2 V2 minus P1 V1 divided by 1 minus N. Professor, haven't some smart people already done this integral and stuffed it somewhere in the textbook and I can find it when I need it? Yeah, but you still need to be able to do these calcs, okay? Otherwise, just turn yourself into a technician, right? You're an engineer. Want to be an engineer, not a technician. So that's the equation for the work. That work is for the process, what? The polytropic process, PV to the N. Now, there's a restriction. What happens, this N cannot be equal to 1. If N is 1, what does that answer look like? Blows up and you have an error. So what you do is you backtrack and you find out right here. When N is 1, you have the integral of CV to the minus 1 dV. True? Or maybe it looks better if I leave it as 1 over V. So if N is equal to 1, that's what you get. Well, what's the integral of C 1 over V dV? Ow, that hurts. Natural log, you're absolutely right. So it's a C natural log of V evaluated V1 to V2. True? Yeah. And so it's that constant natural log of V2 divided by V1, because I know there's a rule where you can get the two together, right? V2 minus natural log of V2 minus natural log of V1, and then you put them together as a ratio in one natural log. So there you go. That's the other work. So let me scoot down just a little bit. Oops. That's a little bit more than a little bit. So when N is equal to 1, the work is equal to C. Well, what was C? It could be P1 V1, natural log of V2 over V1. Or it could be P2 V2, natural log of V2 over V1. One of those, either one works, because C is either P1 V1 or P2 V2. Good? Very good. Let's press forward. No, I don't want to solve a problem. Heat transfer. I know we put the two words together, but really heat doesn't need the word transfer to follow it. Heat is the transfer of energy because there's a temperature difference. But in the vernacular, we say heat transfer, right? Right? All right. So here we have conduction. You have a wall, a solid wall. Maybe it's hot on one side and cold on the other side. Represent the temperature on one side, the temperature on the other. You have a temperature profile from hot to cold if you're plotting temperature going like this. And because it's hot on one side and cold on the other side, you have a heat transfer, Q. Sometimes they'll put Q dot because it's a rate of heat transfer. It's equal to a constant of proportionality known as the thermal conductivity of the material. Some material transmit heat very readily. Some resist the transfer of heat. They have a low conductivity. Okay? Times the cross-sectional area divided by the thickness, L, of the wall, times the temperature difference across the wall. I think the book puts a dot on top of it, right? Q dot. But when you get to the next class, ME3293 heat transfer, everything would have a dot on it because everything's a rate, so they strip all the dots off. And then that's confusing to the student because you say, hey, I was in Thermo 1, Q was kilojoules. I go to heat transfer, Q is now kilowatts. I'm just pointing out your future here, letting you know. But in this class, we put the dot on because it's a rate. How about convection? You have an object, maybe this hot object is sitting here, and you have nice air blowing down and over it. That's why you put fans in computers, and you blow fans in your homes, and you blow fan over your hot body. Anyway, this temperature of the surface is very hot, and you have the temperature of the fluid. A lot of times they put infinity, meaning far into the fluid, not real close to the surface. But far into the fluid, it's a bulk temperature of the fluid. And they say the rate at which heat is transferred, Q dot, is equal to a convection coefficient. Hey, that's a constant of proportionality, just like K. K, thermal conductivity, H, convection coefficient. The area of the surface of this, where the air is contacting the solid, that contact area, times the temperature of the surface minus the temperature far away in the fluid. Q dot. That's a convection heat transfer. All right. Radiation. Well, you have your hot object sitting like this often, and it's at a temperature TS or something, TS. Okay. And you want to, it's always sending out photons. Anything that's above 0 Kelvin, which is everything, is sending out photons. And if their photons are flying back and forth. A lot of those photons are not in the visible spectrum. You can't see them. But maybe you work for the military and you get a special glass, right? They'll let you see into the infrared region to translate that into the visible region so you can see warm things at night or even warm things during the day. True, an infrared camera. But there's a whole electromagnetic spectrum out there. And photons of all surfaces are emitting, okay? Now, what you're seeing right now is not the thermal radiation emitted from the wood walls in this room. If you turned the lights off, it'd be black. We wouldn't be able to see the walls because nothing in the visible spectrum would be coming to our eye. What's visible coming to our eye is the reflection off of the lights, right? That's trying to help you put it all in perspective. All right, but if I go to my house and I have a burner on the stove and I turn it on, I don't see it if it was in a dark room. But later on, I would see it glow. What type of color? Red, because it starts to bleed into, it's getting hot enough to bleed in to pump out photons where my eye can see it. And you start red, indigo, blue. Oh boy, Roy G. Biv backwards. I got it, Get red, orange, green. Oh boy, Roy, red, orange, yellow, green, blue, indigo, violet. I got it. There you go. All right. So it starts to pump out red. And if anybody, and there's probably some in this room, have seen white hot. Yeah, as metal and other things. But anytime, don't look at the sun very long. It's white hot. It's so hot, it's pushing out all over the visible spectrum, and it's all white. So, but don't look at the sun. Okay, professor told me to go stare at the sun, and now I'm blind. So let's put something far away, maybe the sky. We'll call that the temperature T infinity. It needs to really be something out there to send some photons back. And when they exchange photons, the rate at which they exchange photons is given by the Stefan-Boltzmann law, which is given, I'm just going to forget an emissivity of the surface. Different surfaces have different conditions. Let's just say it's a black surface. Sigma, the Stefan-Boltzmann constant, the area, the temperature of the surface to the fourth power minus the temperature of the other surface to the fourth power. And that fourth power is extremely unique. You don't see many things in engineering where there's something to the fourth power that's a law. But that's the Stefan-Boltzmann law. I hope you enjoy heat transfer when you get there. All right, it's a great class. A lot of interesting topics. And oh, by the way, anything hot like that, you're working on a team of engineers, where is the fingers all going to point when they say we have a thermal issue here? They're all going to point to the civil engineer? No. They're going to point to the mechanical engineer. You got the power, you got the anything to do with energy, and now you have everything to do with heat. So yeah, all right. So that's the radiative rate of exchange between them, a net radiative exchange Q dot given by the Stefan-Boltzmann law. we have forms of energy. These forms, we're interested in really just the macroscopic forms of energy. The kinetic, what was that? 1/2 mv squared. Potential, mgz. Internal, if it's hot, it has high internal energy. If it's cooler, it's a lower internal energy. Think it's related primarily to temperature, but not exclusively to temperature. Okay? It's really one way to define internal energy. It's the macroscopic form of energy that's not kinetic and not potential. You sort of define it by what you're not. But we use the symbol U for internal energy. And at this point, let me just say, if it's hot, it's high in internal energy. Okay. We have energy transfers by work. We have energy transfers by heat. At this point, you would just take the rate of heat transfer and integrate with respect to time, and you would get the amount of energy transfer by heat. If you wanted to do it from first principles, conduction, convection, Fourier's law, Newton's law of cooling, or the Stefan Boltzmann law. It'd be a lot of work. We don't do that in this class. A lot of times we just say, we're able to figure it out. It's so many kilojoules. Okay? But the work, so you could do the integral w dot dt. That's no problem. But a lot of times we do the integral of p dv, or we do the integral of f dx. We can get that from first principles pretty well. Okay? In this class, Thermo 1, we can do a lot with work, but we don't do a lot with heat transfer. It's kind of less a cue. Oh, it's given to us, or we're easy to calculate it. Now we have an energy balance. Energy is something, it's a property of our system that's conserved. It's a bookkeeping job. You are now a bookkeeper. You need to keep track of energy and to balance it. So what we do is we write an equation. We say Q into our system. Amount of heat into our system from initial state 1 to final state 2, minus any work that goes out of our system during the process, has to then have a tallying up such that you know either the internal energy went up or down, there's a change in internal energy, or there was a change in the kinetic energy, it went up or down, or a change in the potential energy, but it just didn't disappear. The energy has to balance. And so here is our first law of thermodynamics. It's for a closed system. What do you mean by closed system? Remind me, what does closed mean? No mass transfer. Does it mean no heat transfer? No, you could have heat transfer. Does it mean no work transfer? No, it does mean you could have work transfer. Does it mean it has to be constant volume? No, the work could actually be a boundary work where you're expansion or compression of the system. But this is the first law. Let me try and read it. Energy transfer in, energy transfer out. In minus out. That's both transfers. What is this? This is a change of the energy of the system, and we only have 3 macroscopic forms: potential, kinetic, internal. That's our first law. We solve a lot of problems with this first law. So for a process, let me rewrite it. Q minus W equal to delta cap E, which is a short way of writing delta U plus delta KE plus delta PE. What do they do with this? They said all forms of macroscopic energy. So it's internal, kinetic, and potential. I don't really like to use this too much, but the book uses it, so I expose it to you. I like to sort of slug it out, and sometimes this is 0, and that's 0, and that's 0, but whatever, you have to solve or apply it for each problem. But this is for a process between 2 states. What about a differential? Infinitesimally small amount of change. We can still do an energy balance. We would do infinitesimal amount of heat transfer in minus infinitesimal work. Hey, what is this funny little character right here? Greek delta lowercase. Hey, what was this right here? Greek delta uppercase. Yeah, that's what it is, right? True? All right, let's go on. And that's equal to delta, not delta U, du plus dke plus dpe. So that's our small, instead of a finite process, infinitesimally small process, where there's still some change, but it's very close. Now, if we want the rate form of the first law, guess what we do with this equation? We just divide by the time step, or the small time step. So we have delta Q over dt minus delta W over dt equal to du dt plus dke dt plus dpe dt. So this becomes Q dot minus W dot equal to the time rate of change of du dt plus time rate of change. Here, I'm tired of writing. I'll do the shortcut just like the book. Right? That's what the book does. Call it cap E. All right? Okay. That's the rate. So you have three forms of the equation, forms for the energy balance for a closed system. I'm tired. You're tired. Let's call it a day. We'll pick up there next time. Thank you.